The significance of forged parts in numerous technical areas is demonstrated by their wide range of applications. No vehicle is driven without the aid of forged parts. They're primarily utilized as components in the engine, transmission and suspension. Forged parts transmit forces and motion, are dynamically highly loaded and totally reliable. Approximately 75% of drop forged parts produced in Germany are sold domestically, while the remaining 25% are exported throughout the world. The primary customers are the automobile industry and their system suppliers, as well as mechanical engineering sectors. The percentages refer to domestic supplies measured in tons. The durability and characteristics of suspension systems are tested on dynamic testing rigs. In commercial vehicles too, numerous forged parts operate at high stresses with high loads, as pictured in this front axle application. Numerous forgings are also used for heavy-duty diesel engines and gearboxes in commercial vehicles, or for trailer hitches. Forged parts are used in the most highly stressed places of wear for heavy construction vehicles and machines for structural engineering. For example, numerous components for Caterpillar suspension systems are forged, as are excavator teeth. Forged parts with absolute operating safety and reliability are needed in ship and stationary engines, such as crankshafts, connecting rods, camshafts, tilting levers, valves, and fuel injection nozzles. Large steam turbines in power stations are equipped with forged shafts and turbine blades made from high-temperature alloys. As shown here for a diesel train, railway car applications for forged parts include engine components and safety parts of the undercarriage, such as wheels, axles, and brake components. For aircraft construction, parts are forged from steel, aluminium, or titanium, and include jet engine parts of high dynamic and thermal load, such as shafts and high-precision turbine blades, as well as parts of the landing gear. Rolled semi-finished bars are used in the manufacture of steering knuckles for vehicles. The forging blanks required are cut by shears and are heated to forging temperature by an electronically controlled induction furnace, in the case of steel, to approximately 1250 degrees Celsius. Preforming is performed on a reducer rolling facility equipped with an automated manipulator. The material is fed through the roller sets in several passes. Then an upset forging process for the material starts with a preforming press, followed by a bending process. In the next process stage, the steering knuckle is pre-forged on a forging press. By now the shape of the component is nearly completed, and finally forged in the finisher die. The flash, which is technically necessary, is trimmed on another press in a subsequent operation. The finished steering knuckle and trimmed flash. The first impressions are then hot sized for the subsequent machining process. Controlled cooling from the forging temperature ensures the required mechanical properties of the part. In a final quality test, safety parts, such as these steering knuckles for passenger cars, undergo eddy current testing, fluorescent crack detection, and measurement verification on a multi-feature measuring device. All inspection data are documented. The automobile steering knuckles are now ready for delivery. Peeled steel bars are the raw material for differential bevel gears for passenger cars. The precisely weighed sheared pieces, which have been induction heated in a protected atmosphere to 980 degrees Celsius, are placed into the die by robot. They're single-stroke flashless forged. An infrared measuring beam controls the ejection of the forged bevel gear. Then comes the controlled cooling process. The ready-to-fit gear toothing of the precision-forged differential bevel gears is shaped by a cold calibration process. In automatic multi-stage presses, round bars are heated to forging temperature and, after shearing, formed in several steps into accurately measured forged parts. The slow motion illustrates the manufacturing of an axle stem for passenger cars. Mechanically controlled tongs convey the parts from one station to the next. This axle stem is manufactured with minimal draft. In hammer forging, the heated bars are transported by a conveyor to the double-acting hammer, pre- and finish forged, and trimmed. In this case, 2 forgings are made from 1 bar. Afterwards, the workpiece is clipped. Still hot, the clamp for an auto trunk hinge is bent into the final undercut shape. After shot blasting, the clamp is calibrated, punched and gauged for measurement conformance. The linked production of passenger car crankshafts also starts with billets, induction heated to forging temperature. The corners are flattened and the surface is descaled. The pre- and finish forging of a 5-cylinder crankshaft is performed in plain dies. Afterwards, the workpiece is clipped, the flash goes to the scrap bin, while the crankshaft is transported to the next station. A twister, an operation in which 5 strokes of the shaft are properly aligned relative to one another by twisting. The final operation in the production of crankshafts is hot sizing. During this process, the crankshaft receives its required accuracy in form and dimension. The dimensions are automatically tested and documented in accordance with a sampling plan by a 3-coordinate measuring machine. The manufacture of an axle stub for commercial vehicles begins with the setting of a header. Then the axle stub is drop forged using a counterblow hammer. After clipping, the tubular stepped inner contour of the workpiece is formed on a hydraulic press by means of hot extrusion. The tip of the punch glows red during the process. Hot sizing follows. These axle stubs are manufactured with a combination of drop forging and hot extrusion. The correct mass distribution during the manufacture of a front axle beam is achieved through reducer rolling. The workpiece, with a mass of more than 100 kilograms, is fed by a manipulator through the roller set in several passes. Then it's transferred to a hydraulic preforming press. The workpiece is bent and the final shape of the axle beam is already visible. The preformed part is put into a forging die by a manipulator. And is finish forged in a counterblow hammer, the die halves of which move towards each other. An additional manipulator extracts the workpiece from the die and puts it into a trimming tool to clip away the flash. Finally, the front axle beam for a commercial vehicle is sized, removed from the tool, and placed on a floor conveyor by a robot for transport. The annual production of the German forging industry amounts to around 2 million tons of forged parts, approximately 2/3 of which are drop forgings. The production of 7 common forged parts has been shown so far. Additional massive forming processes will now be explained. By cold extrusion, symmetrical, solid and hollow parts can be manufactured with increased precision on either manually operated machines or fully automated machines when higher volumes are required. Forging on horizontal upsetting machines is a forming process utilizing 3-piece tooling. The workpiece is fixed between 2 clamps and formed with the punch. Afterwards, it's clipped lengthwise and widthwise. This is the only forming process which is capable of manufacturing the undercut form of an excavator tooth. Ring rolling uses a pre-forged and punched disc to form a seamless ring on a ring rolling machine using partial forming in a roll gap. Open die forging is a forming process with free-form tools. Hammers and presses are utilized to partially form the workpiece in multiple strokes. For example, auxiliary dies allow for the formation of a shaft with 2 stems. Manually operated or automated rail or free-moving manipulators can move open die forgings safely and easily, even with a weight of over 100 tons. Forged parts come in a tremendous variety of shapes and sizes. The wide range of forgeable alloys and various heat treatment procedures enable an optimal adaptation of forging characteristics to the various applications. The processes of manufacturing forged parts guarantee consistent process control. The outstanding mechanical properties of forgeable alloys and the resulting high loading capacity support the trend towards lightweight construction, which is increasingly important. Forged parts are free of surface and internal defects, demonstrate reliable material characteristics, and can be manufactured to extremely accurate dimensions. Forged parts show high levels of machinability. Often they're sold as ready-to-fit components or as parts of systems. When subjected to high loads, wear-resistant components are required, for example, for vehicles. Only forged parts allow this. This film has provided just a brief overview of the manufacturing methods and the wide range of applications for forged parts. The German forging industry utilizes all kinds of manufacturing processes and is capable of supplying economical products of all descriptions as a result of its developmental capacity. Further information is available from these sources.